All right, so I'm Andrew Herron. I'm a staff member in the cosmology group at Argonne National Lab. Everything that I'm going to talk about today is in close collaboration with Matt Becker and postdocs Jonas Chavez-Montero and Antonio Villarreal. And the talk is about a program to do sort of a simulation-based approach to do joint constraints on cosmology and galaxy formation together. And the basic cosmological motivation for this is actually, I think, quite familiar to basically everyone, for most people in this room. There's just very large potential gains that you can get on cosmology if you're able to push into the nonlinear regime of structure formation. So this has been now shown by many groups. There's large potential gains, but the price you pay is you have to do a lot of challenging, detailed theoretical modeling. So there's just this natural trade-off then between the statistical constraining power that you have if you're able to push into small scales and the systematic challenges of being able to make an incorrect prediction for galaxy formation physics. A side benefit I won't have much to talk about besides a big boost in statistical constraining power is that if you're able to get cosmological constraints into the nonlinear regime, then you're able to open up an entirely new window on ways to falsify general relativity that are entirely inaccessible if you stick to the linear or quasi-linear regime. So let's see. One significant side benefit of going after cosmology in the nonlinear regime is that you get really interesting constraints on galaxy formation physics. So in the usual way, if you're using an empirical model to constrain galaxy formation, then you don't learn the fine-grained detailed physics about what gives rise to a given AGN jet. Instead, what you get are robust statistical constraints on the key scaling relations of galaxy formation. And these can be used as boundary conditions for a fine-grained physical model. So this left-hand panel is just one among many examples of a classic use of empirical models for this purpose from a nonlinear large-scale structure. So constraining the feedback mechanisms in a hydro simulation using the stellar to halo mass relation as a boundary condition. So these sort of 1D, these sort of simple models have been extended to many different observables now. For example, this panel on the right shows constraints from a recent paper on using the two-point clustering and its dependence on galaxy size, on putting constraints on the relative size of satellite and central galaxies at the same stellar mass. So I would like to just pause briefly over this, just in the context of this workshop on are we ready for the future? So for me, one of the big lessons from the groundswell of support from the 2010 decadal LSST was that even if you just throw away the cosmological constraints in the garbage, the billion-dollar experiment is still worth its money because of the fantastic constraints that you can get on galaxy formation and time domain astronomy. And so if we're in the context of this workshop, pondering the sort of say the next generation, by the way, people are referring to DESI as a future spectroscopic survey, but like DESI has data now, so I was kind of surprised by that. So I'm more pondering in sort of next generation spectroscopic surveys. There's several different directions that we can take that observational effort. And for me, the lesson from LSST is that you really benefit from being able to jointly do science that spans something beyond just a sort of very narrow cosmological target. So that's also, I think, a way I like to sort of frame this talk. And in case that's not compelling, let me just at least say that you get some really high quality multi-purpose mock catalogs from this effort. So there's really no downside to this laborious, difficult effort of doing this theoretical modeling. So great. So one of the classic techniques for doing this modeling is the halo occupation distribution, the HOD. And there are by now too many different seminal papers on this topic for me to even be able to give a legitimate summary in the span of a 20-minute talk. So the basic idea is that you have some empirical scaling relations that you put into host halos for the number of galaxies that occupy host halos, and you're able to make some nice predictions for the two-point clustering and large-scale structure distributions. It's a function of both stellar mass and redshift. So where the HOD approach gets challenged is when really trying to extend the predictions to sort of multiple tracers at once. So actually one of my favorite HOD papers that I think illustrates this, both illustrates the power of the HOD in terms of the interesting physics that you can learn from this approach, and also the limitations of the HOD. So this is a paper from Jeremy several years ago analyzing cosmos data as a function of both stellar mass and also dividing samples into red and blue. And on the one hand, you can learn these really interesting constraints on things like the red sequence migration rate and the time at which galaxies began to quench and leave the main sequence. On the other hand, you really hit a wall when you're trying to be able to jointly constrain multiple tracers of the density field at once. The root problem is essentially just that you're just throwing away so much information, so much physics that's in these high resolution simulations that you have very little choice but to just introduce a very large number of parameters with flat priors on them. And so, for example, in this paper, every time there was a new redshift slice that was used, it took 27 new HOD parameters to be able to describe that data. And this is nothing to pick on Jeremy for. This is a generic feature of the HOD, actually. And again, it's just because we're throwing away so much physics that's in these high quality simulations. So one sort of relatively new empirical technique that is not plagued by this problem dates back at least to a paper by Matt Becker in 2015, but now many variations on this. Joanne Cohn had a version of this same paper, of the same kind of model rather. Ben Moster, this emerge model. Universe Machine is another relatively recent effort along these lines, in which empirical models are built on top of synthetic merger trees. So this is still an empirical approach in that there's no attempt to model the fine-grained physical processes of a galaxy formation, but rather you statistically constrain the relationship between simulated merger trees and their assembly and galaxy assembly. So on the one hand, I think this is a really promising sort of new direction for being able to take nonlinear structure formation constraints, but it's still extremely expensive. So one real challenge that we faced with Universe Machine was just that it took forever to took a very large number of compute hours to get converged MCMCs. And one of the big reasons is just that this approach towards empirically modeling galaxies into merger trees is just fundamentally heavy. So if you want to make a prediction at redshift 0, you have to march all the way down and accumulate all the stellar mass that begins at the beginning of the simulation all the way down to redshift 0. So you have to carry all these arrays around, and you need a supercomputer even to make a single prediction at redshift 0. And then, so another problem that has not yet, I think, been addressed either by this or by HOD style models is just that you have a stochastic likelihood evaluation, which makes it very hard or impossible to be able to compute gradients, which have many, many benefits. We've already heard some of those talked about today. And so what I'd like to talk about is a sort of new way to tackle this problem that sort of gets around some of these computational challenges, but tries to maintain a lot of the predictivity and a lot of the ability to extract information from multiple tracers at once. So one of the classic ways to get around just raw compute woes is building emulators. So when you're limited by time to prediction, then one way to sort of get around this issue is to tabulate what you're trying to predict across the parameter space of your model and to build a Gaussian process emulator. So this is the approach to this sort of compute limited problem dates back at least to in cosmology to the mid 2000s, and it's now become an industry standard technique for being able to make high accuracy predictions with efficiency. So I think Jeremy may show this very slide in his talk, so I won't say too much more about this. This is just an example of how two-point clustering varies as a function of HOD parameters. So the approach that I'm going to describe, so some of the limitations of this approach are just that still we have this problem with Monte Carlo realization noise. So when you build your emulator, you still have this stochastic evaluation of what the data vector should be. And so that's it's not an insurmountable problem, but it becomes especially difficult to address when you're trying to constrain models that are in higher dimensions. So beyond just maybe a handful of 10 parameters. And then another challenge of using Gaussian process emulation in higher dimensions when your model has more than 10 or so parameters is just that GP just really does not scale to higher dimension. So because of the very steep scaling between the number of training points that you need to train a GP and the time to train, then you really hit this wall of around 10 or 15 parameters, and it's just extremely challenging to build a Gaussian process emulator beyond that scale. So, and then maybe this is more of a practical matter, but it's just GP emulation is just poorly suited to exploratory work. So every time you have some small variation in a summary statistic, or if you want to explore a different summary statistic, you have to go and train a whole new emulator. So this is just a very tedious way to go about a whole bunch of different interesting science questions where you don't know in advance exactly what summary statistic is the optimal one. So those are some motivations for the approach I'm going to describe, in which we still are building sort of surrogate functions or GP emulators. So I'm gonna use this word surrogate function throughout this talk, and really just think of that if you're used to Gaussian process emulators, it's just another, essentially a synonym, but it's not just Gaussian process emulation. So it's where you have a model for your model. This is a surrogate. In this approach, the surrogate functions do not stand in for the data vectors. So instead, you build a surrogate prediction for the galaxies that live in the halos. Okay, and then you compute the summary statistics exactly once you have a synthetic mock that you've made into your simulation. And the way you compute them is from your surrogate function actually gives you a PDF of the galaxy properties that live in the PDF of the properties that live in each galaxy. And then you compute a PDF weighted summary statistic from your forward model. So if you have a surrogate model like a neural network that's perfectly differentiable, and you have a summary statistic which is PDF weighted, then absolutely everything in sight is perfectly differentiable. So your data vector is essentially just a giant sum of C infinity functions, and so everything is. So you can compute gradients. You can run Hamiltonian Monte Carlo. You can take advantage of contemporary techniques for optimization and inference if your model is differentiable. So that's one of the big benefits of doing things this way instead of emulating the data vector. So here's sort of a cartoon sketch of how this works. So you have your simulation full of halos, and you have a sort of cheap, short neural network that is attached to each individual halo. And in the simplest case, this could just be, your neural network could just be essentially just giving you the stellar mass, in which case you would just be using a neural network rather than an analytical fitting function in order to predict the stellar halo mass relation. Or it could be something quite complicated, like, for example, how if you model some native quantity for morphology, how you would observe with the dark energy survey, what observed morphology corresponds to that predicted morphology. So in case that sounds impractical, let me just at least comment that training these networks for this purpose is actually very easy. This is the regime that you want to be in if you're doing machine learning. So you have very, very high quality training data. So for example, say you're building one of these surrogate models for a semi-analytic model. Well, if you have some parametric family of solutions to the semi-analytic model, then the accuracy of your training data is essentially only limited by your numerical integrator. So you have very high quality training data, and you have very large volumes of training data, right? So while it's impractical, for example, to run something like Galacticus on a cosmological suite within a live MCMC, you can still run it once. You can still generate millions of training points, of very high quality training points, very accurate training points. So for this kind of prediction, if you're trying to predict, for example, something like a few broadband flux observations of galaxies, then you really only need one or two dense layers in order to be able to get a very high accurate prediction with high quality, large volumes of training data. So this is really, I think, sort of within bounds of even contemporary compute. So the way this looks in a simulation is essentially now you have just this little cheap neural network that's attached to each individual halo, in this case, subhalo. And what you do is you just, in a sort of pre-processing step, you pre-train your surrogate function. And you attach this pre-trained surrogate function to every halo and subhalo. And then to make a prediction, then you just batch evaluate these pre-trained networks on all of the halos that are in your box. So you have a simulated field of halos, you pre-train your surrogate functions, and so the way that this sort of program works, the reason why I'm calling this sort of hierarchical surrogate modeling is just that you don't actually vary the parameters in your MCMC of your surrogate function. Rather, you vary the parameters of the galaxy halo connection that give you the sort of true native theoretical quantities that are mapped onto the halos. And then you use your surrogate function to be able to say, well, how would I observe with some particular instrument this true galaxy that I only have, that can only observe with a given telescope or spectroscopic instrument. So at the end of this pipeline, you have your universe of galaxies with PDFs of the galaxy properties that you are going to use to select your sample to be able to make your measurement. The way you then just weight these synthetic galaxies is just by the sample selection function integrated against the PDF that you've modeled. Okay, so that defines a weight on each galaxy. And now you just use the your PDF weighted estimator instead of your hard sort of discrete counts and hard edge bins estimator that we're used to using when building these GP models. And the end result is just a fully differentiable forward model that gives you apples to apples comparisons to data. So let me give an example of that. So for example, this is one of these hierarchical surrogate models in which we're using synthetic merger trees. And in this pre-processing step, you come up with an analytic fit, an approximating function for the assembly history of the halo. In this case, this is just the mass evolution and the Vmax evolution jointly. So every halo is now approximated with some best fitting model in a pre-processing step. And now what you do, now that you have the full assembly history of every halo, well, then you have an empirical model that connects the assembly history of halos to the assembly history of galaxies, okay? And so then when you have an assembly history of galaxies, then for example, if you have a model for stellar population synthesis, then you can predict what the flux of that galaxy is that lives in that, you can predict what the flux of the galaxy that lives in that halo is. So how do we validate this kind of approach? So one way to check to make sure that you have a sufficiently flexible model is to be able to try and recover the results, for example, of a hydrodynamical simulation or semi-analytic model that's based on entirely different assumptions than the assumptions you put into your own empirical model. So this is just a demonstration that with this sort of approximate halo history approach, that for the case of universe machine, we can get very accurate approximations for the star formation history of universe machine galaxies for, let's see, several different masses, both for quenched galaxies and for present day main sequence galaxies. So universe machine gives us one sort of validation data set we can use to try and establish that the model has sufficient flexibility. Illustrious TNG is again an entirely separate model predicated upon quite independent assumptions. So this is a hydrosim, whereas universe machine is an empirical model. So again, we have perfectly good recovery ability to just sufficient flexibility to capture the star formation histories of quenched and star forming galaxies of different masses in illustrious TNG. So that's true for median. That's true for median star formation histories, and it's also true for individual star formation histories. So here's one roughly Milky Way type galaxy in universe machine, and another one in illustrious TNG, and then surrogate model going essentially right through the noisy fluctuations of the star formation history of the galaxy. So going beyond one-point functions and historical evolution in order to validate this sort of empirical approach to galaxy formation and cosmology. Of course, we want to be able to do cosmology. We're going to need to be able to use two-point functions as our constraints. So this is an example of for a couple of different stellar masses at redshift to half. This is the correlation function of quenched in blue. This is star forming autocorrelations, then also the red-blue cross for two different stellar masses. And again, the really nice thing about this hierarchical surrogate modeling approach is just that these predictions for the two-point functions are fully differentiable. So this is a two-point correlation function where you can actually analytically write down, it's just a giant sum of C infinity functions. So you can analytically, in principle, write down what the derivative of this is with respect to your model parameters. That's really laborious. You can do it. So what we've been using is the deep learning library JAX to do automatic differentiation. It's essentially an automatic differentiation library that exposes these gradients of these complicated predictions in a very, very fast way that also scales very, very well with GPUs and TPUs. So this is one of the really significant benefits of going after large-scale structure with a differentiable model. And this particular formulation just lets you leverage essentially these really high-performance deep learning libraries, provided you're able to formulate your model in a way that these libraries essentially support the API. So let me see. I think I'm gonna have to skip. So just like you can do with two-point correlation functions, you can have sort of fully differentiable predictions, for modeling predictions for cluster observables. I think I'm gonna have to skip over this in the interest of time. Great, so I mentioned briefly one of the sort of flavors of this kind of surrogate modeling that you can now tackle is forward modeling SEDs. So for example, if you have an SPS library, for example, this is both of these plots are taken from actually this plot is taken from a recent paper led by Jonas Chavez Montero. He's a postdoc at Argonne. This is from a SPS library that he's been working on called GalaxPy. An SPS library is essentially just, it's a physical model for how this evolution of a galaxy's star formation history, together with parameters like dust and metallicity, give you the SED of a galaxy. So again, any individual galaxy is a kind of, you have to do some nested integrals that are kind of nasty and expensive to be able to do live in an MCMC, but you don't need to do these SPS integrals on the fly in an MCMC every time. In a sort of one-time only step, you can build a neural network approximation to an SPS library in a pre-processing step. And then if you have a model for an empirical model for star formation history, like what I just showed you, well, now you have a differentiable model for stellar population synthesis. So along the way, one of the things that we've learned in studying these differentiable predictions of SPS is just that actually the relationship, at least in terms of the redshift 0 optical colors, the relationship between star formation history and redshift 0 optical color is very, very simple, it turns out. So what you're looking at here in each panel in this left-hand figure, each panel is a different sort of color diagram of what the color space spanned by universe machine galaxies looks like in Sloan. And each arrow corresponds to the change in color space that corresponds to a change in universe machine star formation history. As you can see, they all, for all different masses and for different colors, they lie along a single universal direction in color space, which is just to say that the relationship between star formation history and galaxy color is actually remarkably simple. Even though each broadband color changes in a different way, if you look at for example, the principal component decomposition of how the color space, how you change in color space with star formation history, it's very, very simple. It's nearly a single dimension. So great. I think I'm gonna have to skip over. So one question you might wonder about is what about the wiggles? Are they important? So for example, I showed this smooth model passing through a noisy star formation history, right? So if you're trying to predict, for example, the emission line of a particular galaxy, you might be concerned that if you miss a given wiggle, that you actually won't get the emission line of that particular galaxy in that particular halo correct. Of course, as cosmologists, we're not trying to predict the emission line of a particular galaxy. We're trying to make statistical predictions. And so this actually may not be a worry, but it does depend on what you're actually trying to predict. So at least in terms of predicting optical colors, this turns out to be a very, very tiny effect for most bands, especially beyond anything redder than U band. So on the right-hand panel, this just looks at the difference between the broadband color that you would get if you exactly integrated one of these galaxies that I showed you to predict their broadband colors versus with the surrogate function. And it's really only like 0.01, 0.02 mags outside of U-band, and even for U-band, it's maybe 0.03 or 0.04. So all possible galaxy observables you might not be predictable in this way, but we get to choose which galaxy observables are the robust ones that we use to constrain cosmology. And so for me, this is at least a very promising early indication that we can go very, very far towards being able to predict at least broadband color-based selection functions with a very simple surrogate function approach. So Johannes has conveniently just talked about this. So this is the way in which, so everything I've been talking about so far is all done at fixed cosmology, right? So you run one fixed simulation and then you apply this surrogate modeling approach on top of the fixed box, and then make your 2-point function predictions. But if you have a suite of cosmological simulations, then you can do exactly as Johannes just described, and then run your MCMC to convergence at each fixed cosmological box, and then use cosmological evidence modeling to be able to get your cosmological posteriors. So it's essentially the same thing that we've been doing at fixed cosmology, now extended to get cosmological constraints just by being have a cosmological suite that you run MCMCs throughout the space throughout the cosmological parameter space, and then in this post-processing step, you then build a surrogate model for the cosmological dependence of the evidence. So Johannes just talked about this. I won't prattle on too much longer about that. The basic role in this program of traditional semi-analytic models and hydrodynamical simulations is essentially that they provide validation data sets that are really critical to be able to give you confidence that not only is your model sufficiently flexible, but that you don't get a biased result from the residuals of cosmology, from the fact that you're not perfectly describing galaxy formation physics with a surrogate model. So there's more I could say about that, but I think I need to conclude with just a wish list for what I'm thinking of as future surveys, surveys that have not yet begun taking data, but that I think should very much be under discussion at this workshop, with sort of what is the character of the next sort of DESI successor that we should be sort of looking for. And for me, my interest is really in, well, doing cosmology and galaxy formation jointly together. And I think this hierarchical circuit modeling approach is one way that we can extract a whole lot of information, both about cosmology and galaxy formation at once, and in a way that really gets around a whole lot of the computational problems that have prohibited this so far. And one of the main ways that, one of the main sort of enabling features of this is that the models are fully differentiable. So you can take advantage of gradient-based optimization algorithms, Hamiltonian Monte Carlo, and on. So I think maybe I'm out of time, so I should conclude before I say any more. So thanks.
Time for maybe one quick question.
Yeah, the models may be dimensional, but they're very expensive with power.
I mean, for example, I mean, Johannes is doing this now when he was just describing. So, I mean, there's been many papers doing this, doing a Monte Carlo type mock population where you have to compute a 2-point function on the fly. And it's true, it's expensive, but I mean, for example, for a Sloan volume survey, you can do this in 1 or 2 CPU seconds. You can do this on a laptop. Well, right. So this program really doesn't require, the cosmological information doesn't require you going out to, like, for example, 500 megaparsecs. So if you only require getting correlation functions out to 30 or 50 megaparsecs, then that's actually totally within bounds. Again, that's even with modern compute. So even for Monte Carlo mock population, we're not really CPU limited in terms of computing 2-point functions. If you want a power spectrum out to 500 megaparsecs, then yeah, it's much more expensive. But the constraints for this approach to the problem don't require that.
All right, let's thank Andrew again.
So next is BV. My name is BV Dai, and I'm a graduate student here in UC Berkeley. Today I'll talk about improving the halo field and generating stellar field from low resolution body simulations. The analysis of current and future spectroscopic surveys requires accurate modeling of galaxy distributions. Here I list 3 major ways of producing realistic galaxy maps. The first way is to run hydrodynamic simulation, but this is often very computationally expensive, and I will not talk about this in this talk. We could also run n-body simulation, obtain the halo catalog, and then apply semi-analytical models such as HOD and halo abundance matching. The first part of my talk will fall into this category. I will introduce a new halo finder that could improve the halo statistics in low resolution fast simulations. The third way is to use machine learning approach to directly model the galaxy distributions or other hydro outputs from n-body simulations. In the second part of this talk, I will introduce a physics-based machine learning model to produce stellar maps from its underlying dark matter distribution. So let's firstly focus on the halo field. Combining n-body simulation and semi-analytical models have been widely used and achieve lots of success in current surveys. So why do we still need to study this topic? Let's take DESI for an example. DESI aims at measuring ELG up to redshift 1.7 and LRG up to redshift 1. To accurately model these galaxies, we need to resolve 10 to the 11 solar mass halos in the simulation. And also to cover in the entire volume of the survey, we need a 3 gigaparsec box. Now let's assume we are going to run an n-body simulation to meet these requirements. To accurately modeling this 10 to 11 solar mass halos, we need at least 200 particles in these halos. So that corresponds about 5 times 10 to the 8 particle mass resolution. And considering the box is 3 gigaparsec, the total number of particles will be 6 trillion. And that is very expensive to run. So in this research, our goal is to develop a method to generate accurate halo catalogs from low resolution fast simulations. So let's firstly take a look at why the halos in those low resolution simulations are not accurate. Here I show the same halo in different simulations. In the left panel, this is a high resolution multi simulation. The right panel is also a full multi simulation, but the resolution is 8 times lower. And in the middle panel, I show fast PM, which is a fast approximate embody solver, and the resolution is the same as the red panel. We see, all those red crosses are the centers of halos identified using a friend of friends halo finder with 0.2 linking length. And we see that in those low resolution simulations, the halo is breaking into 2 or 3 small halos because the particles are not concentrated enough. So how do we solve this problem? The simplest idea is to increase the linking length. If we have a larger linking length, we should be able to connect all the particles and produce the correct halo. So here the blue cross show the halo identified using a larger linking length, and it's very close to the true position of the halo, which is shown in the yellow dashed cross. So this is the basic idea of our relaxed friend of friends halo finder, where we allow different linking lengths for different halo mass. For small halos, which our simulation cannot resolve very well, we will use a larger linking length. And for large halos, we just use the standard 0.2 linking length. One problem with this large linking length is that it will find lots of fake halos in the high density region, which are just some particles that are close to each other, but are not gravitationally bound. Here we try to solve this problem by using the velocity information to reject the fake halos. We will reject the halos if its velocity dispersion is too large compared to this scaling relation. And finally, we'll also find the resolution of initial condition to be quite important for the formation of small halos. So here we also double the resolution of the mesh for generating the initial condition. In this research, we'll use fast PM, which is a fast particle mesh simulation where it enforces the correct linear growth. We'll run only 40 time steps to redshift 0, and we have a very low mass resolution. There are several free parameters in our model, such as how the linking length depends on the halo mass and redshift, and what is the thresholding for rejecting the fake halos. All these free parameters will be determined by fitting the halo statistics to high resolution body simulations. Here we'll mainly compare our results to TNG 302 dark, which is a dark matter only run, and the resolution is relatively high. We'll also compare our results to TNG 1 dark, which has 8 times higher resolution, and TNG 2, which is a hydro run. The low resolution TNG 3 dark has the same resolution as our fast PM, so we will also take a look at that as well. So let's firstly compare the halos individually. Here we are trying to match the halos from different simulations. If for a halo in our reference simulation, and we cannot find a counterpart for it in other simulation, we will say this halo is missed. And here in this figure, I show the ratio of missed halo as a function of halo mass. Here the different panel is different redshifts. And we can firstly take a look at this brown dotted line, which is the original fast PM. And we see it misses about 40% halos at around 10 to the, thanks. It misses about 40% halos at around 10 to 11 solar mass. So after we increase the resolution of initial condition, the results improves, which is shown in the red solid line. And after finally we adopting our relaxed friend of friends halo finder, the result is shown in this thick purple line. And we see we can see the huge improvement between between the thick line and the original FastPM. Also, we can compare the results with a full embodied simulation of the same resolution. It's shown in this green dashed line. And we can see at high redshift, they basically overlap. So that means our halo catalogs is comparable to a full embodied simulation. Well, at low redshift, our halo catalogs is slightly worse. Here I show the halo bias. The Y panel is the ratio of halo bias over our reference. And the x-axis is the halo abundance. Because here we are matching, we are selecting the halo using abundance matching. And so the small abundance means large halo, and large abundance, small halo. We also show the approximate halo mass in the top x-axis. Here, the color of the line is same as the previous slide. And we can see FastPM predicts predicts a very large halo bias for the small halo end. This is because it's finding a lot of fake halos in the high density region. And after we reject the fake halos, the result is again the thick purple line, and we see it's consistent with the reference simulation. Here we also check the halo auto power spectrum, but here the difference basically is dominated by the linear halo bias. So the information is very similar to the previous slides. I will just skip this one. And we also check the halo matter cross power spectrum. And we see at most redshifts, our result is consistent with the reference. While at the low redshift on small scale, our model is predicting too much power, but on the linear scale, it's doing well. Here we show the halo power spectrum in redshift space. Here we only show the power of K modes along the line of sight. So that's mostly affected by the redshift space distortion. And right here, the small scale velocities of halos in our FastPM is not very accurate. So we also do a velocity calibration. The detail of this calibration, I will not go into the details of this calibration, and I will just show the results. Here we can again see the big purple line is very consistent for our the reference, and compared to the original FastPM, and also the full embodied simulation, which is shown in the green line, we can see huge improvements. So here in this part, we introduce relaxed friend of friends halo finder, where we allow the link length to be a function of halo mass, and we use the velocity dispersion to help us determine if the halo is real or not. We also increase the resolution of initial condition, and we show that all of these improve halo statistics. So for the second part, in this first part, we have improved the identification of halos, which combined with semi-analytical models could connect the observed galaxy distributions to the underlying dark matter distribution. Of course, an alternative way is to directly model the baryons from dark matter only simulations using machine learning approach. For example, people have using GAN or convolution neural network to predict galaxy distributions or gas temperatures. In the second part of this talk, I will introduce a physics-based machine learning model, which is free of neural network, and will show that our model can produce stellar maps from its underlying dark matter distribution. So we will start from the particles from dark matter only simulation, and we'll try to develop a model to mimic the missing baryonic physics. In terms of the stellar field, we are mostly trying to model the gas cooling and collapse, which we can consider this as some matter transport. And we are also going to model the star formation. And we know star formation only happens in the high density region, so that corresponds to some thresholding on the density field. So our model should be able to model the matter transport as well as the thresholding on the field. So let's firstly take a look at the particle transport. Here we will add a displacement field on the particles from n-body simulations, where this displacement field is modeled as the gradient of some transfer function times the density field to some power gamma, where this transfer function is modeled as a high pass filter times a low pass filter times k to some power n. To help us understand why we modeled the displacement field in this way, we can firstly ignore the high pass filter and low pass filter, and we can let n equals -2. So this transfer function just becomes a inverse Laplacian operator. If we further assume gamma equals 1, so this S will just give us the gravitational force up to some normalization. So, and we know if the direction of the gravitational force should tell us the correct direction for the gas collapse. So here, this equation is just a generalization of the gravitational force, where we allow all these index to be free parameters. And we also add a high pass filter and low pass filter to select the scales that we are interested in. After we move the particles, we'll paint the particles on a mesh. And then we'll apply a field nonlinear transformation to mimic the star formation. We'll firstly take the density field to some power mu, and then we'll apply a ReLU thresholding function, which only selects the high density region where star formation happens. Note that all of this B1, B0, mu, n, kl, kh, gamma, and alpha, they're free parameters. So we have eight free parameters in total in our model. And note that this is much smaller compared to a neural network. So our model is much faster to train, and it should be more stable. In a word, our model takes particles from dark matter only simulation as input, and it will firstly move the particles based on local density to mimic the gas collapse. And then we paint the particles after the movement on a mesh, which we call this delta prime. And then we'll apply a nonlinear transformation. In particular, we'll apply a ReLU thresholding function to mimic the star formation process. In this research, we'll again use TNG 300 simulation, which is a high resolution hydrodynamic simulation, include wide ranges of baronic physics. And our input data will be the low resolution dark matter only run. And we'll try to produce the stellar mass from high resolution hydrodynamical simulations. We'll build a 512 cubed mesh for the hydro outputs, the stellar mass, and our loss function is defined as the L1 norm between our predicted stellar field and the true stellar field. So in this figure, I show the results. The top panel is just the dark matter distribution, which is the input of our model. The middle panel is the true stellar distribution from hydrodynamic simulation. And the bottom panel is the output of our model. So this is the learned stellar map. And we can see that, well, in the high density region, our model is a little fuzzier. But apart from that, the overall distribution is much similar. We also show different redshifts. And here in this slide, I show the ratio of the power spectrum of our model stellar mass over the true stellar mass. And we see on large scale, the power is matching very well. Now on small scale, we lose this about several maybe 40 or 40% power. On the right panel, I show the correlation coefficient between our model stellar mass and the true stellar mass. And we see the cross correlation is about 0.9 up to maybe k of 8. So in the second part, we have introduced a physics-based machine learning model to produce stellar mass. And the particle movements and field transformations in the model can be viewed as baryonic physics process. And compared to other neural network-based machine learning model, our model has much fewer parameters to optimize. So in terms of the future work, our goal is to build an alternative to the HOD so that we can work with a stellar field instead of galaxy positions. And finally, just for fun, this model can also produce other hydro outputs. For example, we have tried to produce the gas temperature. Again, this is our learned temperature and true temperature. We can model the KSZ signal, the TSZ signal, the X-ray, and H1. Yeah, that's all. Thank you.
Question for David?
In the, I think, second last slide where you showed the power spectrum ratio,
Yes.
why is it it's worse at redshift 2 than redshift 1? Cross correlation
Cross correlation coefficient.
So it looks like on large scales at redshift 0 they will be fine. Why is it at redshift 2 it's actually worse?
Sorry, you mean the power spectrum or the cross
correlation?
correlation? Sorry, actually, I'm not quite sure about the reason, but yeah, and redshift 2 is relatively lower compared to redshift 1, but still it's, I think the cross correlation is about 0.9, so I think that's a very good cross correlation coefficient.
How does this compare with Zhang 2019?
Oh, you mean GAN?
No, Zhang, the CNN study that you mentioned. I mean, the full neural network.
Oh, right. Actually, it's very hard to do the comparison because here all the resolutions and the reference simulations are different. Yeah, so it's hard to do a direct comparison. But I think the main advantage of our model is the small number of free parameters. Yeah.
The next
40 times steps to is equal to 0.
You mean the first part for the halos? Yeah, actually, for the second part here, we are because this is just the first step of this research. So here we actually use full embodied simulation as the input data. But in the future, we plan to also use fast simulation as input data.
All right, let's thank David then.
Okay, good afternoon, everybody. I'm Joe DeRose. I'm a postdoc at joint between UC Santa Cruz and UC Berkeley. I'm going to be telling you a bit about some work that we've been doing in the Emulation project related to accurate predictions in massive mock catalogs. So just to start, a bit of motivation for why we need emulators at all. We heard a lot this morning about perturbation theory, and I think it's a fairly uncontroversial statement that that basically above k of 0.3 or maybe a 0.4, all perturbative models are breakdown in the literature, at least. But there is strong motivation to try to push to smaller scales. This is just kind of a motivational plot. This is constraining power on two dark energy equation of state parameters, WA and WP, as you vary the minimum scale of clustering and lensing analysis. So the blue contour here is if you use a 50 megaparsec minimum scale, and then the various other contours are smaller with linear bias. These three are all linear bias. The green contour here is then if you push down to 0.1 megaparsecs and marginalize over some HOD parameterization. This is just to say that there's a potentially significant amount of information to be gained by going to smaller scales. The question is just how much there is. So one solution for going to smaller scales is something called emulators. Andrew gave a nice introduction to what this is, but I'll give a kind of an overview again of the basic idea. What we do is we run suites of high resolution n-body simulations that span kind of currently allowed cosmological parameter space. That's kind of put into a cartoon in this figure here, where you have constraints on CMB temperature spectra in the black points, and the different lines here are different cosmologies that are consistent with this. We generate initial conditions at those cosmologies, pipe them through an n-body simulation, and then we can measure fully nonlinear predictions for the matter power spectrum here shown at Z of 1 and 0. The problem with this process is that the n-body simulations are very expensive. They take upwards of 10 to the 4 CPU hours and potentially many, many more than that, depending on the resolution of the simulation. And so we need something that's a lot faster. And what we do is we build something called an emulator or surrogate model, which then takes the measured outputs of all of the simulations that we've run and interpolates between them as a function of cosmological parameters and galaxy formation models. And by doing this, we can produce a model that is very accurate and can be evaluated in hopefully less than a second in order to do standard MCMC type constraints. So this is kind of the recipe that we've begun to follow in the Emulus project. Many of my collaborators are in the room. Jeremy is going to give a talk right after me about this. Zhangzhu is also here. But this is all work that's done within this collaboration. It's not only things that I'm doing. So the first set of papers that we published were based on a set of simulations I'm going to call Emulus Alpha. And the simulations that we ran are kind of depicted in this figure here. The black points are the 40 test simulations that we produced at 40 points that are drawn from a combination of CMB, BAO, and type 1a supernova constraints, as illustrated in the blue and green contours here. And like I said, the black points are the 40 gigaparsec cube boxes with a mass resolution of about 10 to the 10 that we produced. And the red points here are then another set of 35 simulations, 5 at 7 different cosmologies that we ran to test the predictions that were trained on the 40 black points there. So just an example, this is something that we put out, I guess, almost 2 years ago at this point. So an emulator for the halo mass function, and this is following basically exactly the recipe that I mentioned earlier. We ran simulations, we measured the halo mass function in all of those simulations, and we fit a flexible model to those measurements. And so that's just shown here in the top panel here. The points are measurements from the test simulations that we ran, which weren't used to train this flexible model. And the lines are predictions for what the halo mass function at different redshifts in those boxes should be. The bottom is residuals from those test boxes. The solid lines here are our expectation for what the error should be given the sample variance in those boxes. And so you can see we can produce predictions for statistics such as the halo mass function to about 1% at most mass ranges. So things get a lot more complicated when we actually want to emulate direct observables. The halo mass function is just something that you can measure from an n-body simulation. It comes with a lot of caveats, such as the fact that we're running a dark matter only simulation. There are resolution effects. But the things that we really want to predict are actually direct observables in our survey, such as galaxy clustering measurements. And what's often done in this context, really most of the literature in terms of emulation of galaxy clustering statistics is related to halo occupation distribution models. So this figure is just showing kind of a range of choices that we could make for connecting galaxies to the underlying dark matter distribution in our simulations. So halo occupation distribution models are kind of a minimal assumption that you can make for this connection, and basically posits that there is some functional form which tells you the number of galaxies as a function of halo mass, and then you make assumptions for the radial distribution of those galaxies within within host halos, as well as the velocities of those galaxies if you're trying to predict redshift space distortion related statistics. And this is kind of, has been used a fair amount in the literature at this point. Jeremy's going to talk a bit about work that we've done in that front. The thing that I want to spend a little bit of time in the next few slides talking about right now is kind of the next step to the left in this here, subhalo abundance matching. So here we want to take more seriously the predictions that are being made for small scale dark matter statistics in our simulations. In particular, we're going to take very seriously the distribution of subhalos within host halos, as well as the velocities of those subhalos. And we're going to use that to reduce the number of parameters in our models and potentially make kind of more robust predictions that are also easier to connect to a larger number of observables. So one caveat that comes with this sort of thing is that by moving to the left in this diagram, we're placing more faith in our simulation, in the convergence of our simulations, as well as in the galaxy formation physics that we're using to inform these models. So in order to use such a model, we need a higher resolution simulation. Like I said, this subhalo abundance matching models are obviously going to be using subhalos in these simulations. So we ran a set of simulations that is of sufficient resolution to analyze most relevant galaxy samples, at least in terms of slow and main galaxy sample, and hopefully for the DESI bright galaxy sample as well. So this is a suite of 25 high resolution simulations in the same parameter space that I mentioned earlier that we ran the Emulation alpha simulations in. These are 400 megaparsec cube boxes with 2048 cube particles. So that's a mass resolution of about 6 times 10 to the 8. The suite is nearly complete, but what I'm going to be showing you in the next couple of slides is results coming from a simulation of basically similar resolution and same size. It's a small multi-dark Planck simulation, just because that's already in place. But this suite of simulations is, like I said, hopefully what will be very useful for DESI BGS using this sort of model. So just a brief overview of kind of some of the ingredients of subhalo abundance matching. So the goal of this sort of model is really to be able to make predictions for a broader range of statistics in terms of being able to make predictions as a function of, for instance, stellar mass. So what I'm showing in this plot here is measurements from the SDSS main galaxy sample for 3 different stellar mass bins, which are in the different columns here, and 3 different statistics of projected correlation function, monopole and quadrupole. The points are the SDSS main galaxy sample measurements, and the line are the line is the predictions from the subhalo abundance matching model that I'm going to talk about. This is at fixed cosmology because right now we're only using one simulation, but eventually this will be extended to interpolate over cosmology as well. So the model ingredients here are, so actually one more thing about subhalo abundance matching, for those of you that are totally ignorant about the type of modeling that is done here. Basically the idea is you have a luminosity function, or just a set of galaxies that you have in your data. You rank order them by luminosity or mass. You have a halo catalog, which you also rank order in terms of some halo property, and then you just do a one-to-one matching between the galaxies and halos in order to basically assign luminosities or masses to the halos in your halos and subhalos in your simulation. So the first thing that you need, obviously, is to decide on what halo property you want to use to interpolate between, which halo property to use to do the ranking. Here we're just going to interpolate between virial velocity and kind of peak velocity the halo ever achieves. These are kind of 2 well-studied proxies in the literature, and we want to be agnostic to kind of which one we're choosing. So we're going to parameterize that and kind of marginalize over that. The other thing that we need is a scatter between the halo property and stellar mass or luminosity. This is just a log normal scatter. And then the last thing that we're going to need, which isn't often included in subhalo abundance matching, but we find to be necessary, is an orphan model. So I'll talk a bit more about that in the next slide, but we're using anywhere between 1 to 4 parameters here. So in order to fit this full data vector here, we've used 6 total parameters. In order to fit actually just these 2 mass bins, we can use 3 parameters, which is a significant reduction in terms of what you would need from, for instance, HOD, whereas Andrew was saying, basically you need to introduce a full new HOD per mass bin here, or if you want to do different redshifts, that's also an issue for HOD. So a bit more about some of the details of this orphan modeling, which as I said, is very important. So the problem with n-body simulations, well, one of the problems with n-body simulations, even very high resolution n-body simulations, is that you have artificial disruption of satellites, of subhalos. And so that's what this plot is illustrating here. It's a plot from a paper by Frank van den Bosch. So what each of these panels is showing is the fraction of bound mass of subhalos, where one is the total mass that they fell in with, and then on the x-axis you have time, so they're losing mass over time. And each panel here represents a different choice for the number of particles that you allow those subhalos to have, and the force softening that you use in the simulation. So this is a fixed gravitational potential that the satellites are orbiting in. And so you can see these different blue lines represent different realizations of subhalos orbiting in this fixed potential. And the point here is that almost all of them fall below this fully converged black line here. So at a certain time, after a certain amount of time orbiting within some host halo, even with an enormous number of particles, you're going to have artificial disruption in your simulations. But what we can do is we can say we trust that everything that has fallen into a host halo is a real halo. Obviously, we're able to track things before they fall into halos. But then we keep track of them still after they're no longer able to be tracked while they're orbiting in these potentials, and then we call them orphans. And the only thing that we need after that is we need some prescription for then when to say that these orphan halos have actually disrupted. And so in this case, we're going to let that be a function of the peak velocity of the subhalo. Sorry, this didn't come out very well. And we're going to say that as a function of this peak velocity of the subhalo, there's some ratio between the maximum velocity that subhalo has now to its peak velocity at which that subhalo actually disrupts. And so we can fit this model to this clustering data that I was showing you here earlier. And so the constraints on where you need to say subhalos disrupt are shown by these three different lines. The purple and blue lines here are for the more massive galaxy samples, and they're consistent with basically no disruption. So the fact that this isn't equal to 1 is a technical detail, just ignore that. But for the less massive sample here, you can see that you do need a significant amount of orphans because basically you need to keep orphans down to when they've been stripped by a factor of 40 or so, 40% or so. And so there are still some issues with this orphan model. We can fit this lower stellar mass bin with an orphan model, whereas without an orphan model, you can't fit this at all. But the problem is that then if you look at something like a posterior predictive distribution for what the rest of the clustering data vector should look like, conditioned on this data, it is inconsistent with the higher mass bins. So this is telling us that the orphan model that we have currently is not really flexible enough to fit this full data vector. We can either fit this part of the data vector or this part of the data vector. But I'm going to actually view this as a virtue of this model, not the fact that it can't fit this data, but that you can actually make plots like this where you show a posterior predictive distribution of other measurements conditioned on the measurements that you're interested in. And this is a nice way of checking to see whether your galaxy model is able to encapsulate the galaxy physics that you're really interested in. And so this is something that you wouldn't be able to do, for instance, with an HOD model. Next slide. Thank you. So definitely, very much, that's definitely a potential issue, and we haven't incorporated any baryonic feedback effects into this model yet, and that's why we're not doing cosmology with it yet. So there in the literature now, there are a few nice models which claim to be able to encapsulate the baryonic feedback on the matter power spectrum in a few different hydra simulations. And so we could apply these right now. But there's still a lot to understand in terms of how these models connect to velocity statistics and subhalo statistics. And so those are kind of two more ingredients that we're going to need in order to use this sort of model in actual cosmological constraints. Okay, moving on a little bit more quickly because I'm running out of time. The other thing that you might want to do with this sort of model is model galaxy selections beyond mass. Like the ones that most of the galaxy samples are going to be in upcoming surveys. and the problem with galaxy selections beyond mass is that they have potentially very complex HODs. So this plot is just showing the number of galaxies as a function of halo mass from constraints from Hongguo on the EBOS ELG sample. So you can see these look like pretty weird functions of halo mass. It's going to be very hard to say when to stop adding parameters to this sort of function in order to actually fit your data well. So what I'm going to advocate for here is something, instead of just adding parameters to your HOD where you kind of don't have a way of checking to see whether or not you've added enough parameters, you want to connect things back to galaxy formation physics again here. So just an example of this isn't necessarily the model that you want to use to do this, but an example is something called conditional abundance matching, where you add one extra parameter, which is the correlation between star formation rate and accretion and stripping. And here you can make predictions for quenched and star-forming galaxies, which are the red and blue lines here, for a range of mass bins. And again, using things like the posterior predictive distribution, like I was talking about before, you can kind of diagnose as to whether or not your bias model is working well enough. Okay, in the last minute that I have right now, I'm going to talk about another set of simulations that we're running. So the simulations I was just talking about are going to be really nice for low mass galaxy samples. For higher mass galaxy samples, such as the LRG sample and ELG sample in DESI, we're running a suite of simulations called Emulation, which is a suite of 50 pairs of sims in a significantly expanded parameter space that includes massive neutrinos. The expanded parameter space is really necessary because, as you can see in this plot, again, the labels aren't coming out very nicely, but the blue contours here are just kind of for illustrative purposes, but they're the DES-Y1 posteriors on these cosmological parameters. The black points here are the points at which we ran simulations for Emulus alpha. And so you can see, in order to do a cosmological analysis with wide priors that don't take into account CMB constraints, we really need to run simulations in a broader parameter space. So that's what we're doing with Emulus new. The other really nice aspect of this is we're doing kind of these pairs of simulations, one which is higher resolution, which should have the resolution to model ELGs, and then one which is lower resolution but larger. And the nice thing about this is we can play games like what BUA was just talking about, where you clean up the lower resolution simulation to look like the higher resolution simulation, and then potentially even run like a fast PM simulation at higher redshift to get you out volumes where you have maybe source galaxies to do cross correlations with. And so by producing these pairs of simulations and then following them up with lower resolution things to put at higher redshift, we can potentially produce very nice mock catalogs using this suite as well. Okay, so some conclusions. We've run a set of simulations called Emulus beta, which we can use subhalo abundance matching on, and it allows for the modeling of a very large data vector with potentially just 3 parameters, unlike HOD, which you would need you have a proliferation of parameters basically. Conditional abundance matching or some related model might also allow for an extension to beyond mass selected samples. We still need to connect with baryonic feedback. I don't know why the perturbation theory part is a subpoint of that, but the idea here is that on large scales, we will actually basically revert to a perturbation theory based model. And the Emulus new simulations are going to meet the needs of DESI for ELG and LRG samples, as well as allow for nice mocks. So, thanks.
Maybe one quick question for Joe.
So having few parameters is good if you can see the data, but if you cannot, then it's not so good, right? So do you think you can model the RSD to 1%?
Yeah, I mean, it's a good question. There's we need to do a lot more testing on mocks. I think looking at hydrosims is probably a next step. And I think really the point here though is that HOD is maybe not the way to go, just because you're going to need to model similar things in sham and HOD. Maybe you need to add velocity bias parameters or something like that. But at least when you're starting with sham, you're starting from a better place where maybe you have better physical motivation for how to add in these extra parameters. Whereas with HOD, I think you can kind of endlessly add parameters and maybe never really converge on something. But yeah.
All right, let's thank Joe again.
Okay, thanks. So I'm just going to basically pick up where Joe left off, at least with the Amulus project, and highlight some results from one of our papers on emulating nonlinear galaxy clustering. So obviously there have been lots of introductions to this. I don't really have to go into this, but basically to recap that we have these 40 n-body simulations, and then we add extra parameters governing galaxy bias, and this is of course based on HOD, and then we're able to actually interpolate in this space, this extra parameter space of cosmology and HOD, to get percent level predictions for what galaxy clustering will look like. So why do we want to do this? So as has been stated many, many times already, so there is a lot of constraining power at small scales, but there are, we know this, but there are lots of unanswered questions, such as how much constraining power is available at galaxy clustering at small scales? What scales does that come from? Of course, if you're gonna try to model nonlinear galaxy clustering, you're gonna have to add all these extra free parameters that everybody keeps talking about. And once you do that, how much of this information, which we know is there, is actually recoverable? So that's the purpose of this project. And going back all the way to 2014, Beth Reed had sort of a pilot study on this sort of approach, trying to do analysis of nonlinear RSD measurements in BOSS, and found that she actually got an increased precision of a factor of 4 on constraints of F sigma 8. Now, part of this is because in this paper, they actually fixed the cosmology, and which was a limitation at the time because there weren't, we didn't have all this large variety of suites of simulations, but now at the Emulation project, we're able to do this in a more robust fashion. So this is Beth's measurement of the 2-point correlation function, now in 2D, r sigma r pi. And our target spatial range is basically less than 30 megaparsecs, which is basically the range on this plot. And inside that range, you can see both of the different effects in redshift space distortions that you've come to expect. You get the compression from coherent infall at large scales, and then you also can clearly see the elongation from fingers of God, from galaxies that are either probably in high density regions or even in same halos together. Now, I think it was stated earlier on by Misha that the fogs just suppress information, but I actually disagree with the statement. I think there's actually a lot of significant information in the fogs themselves. The amplitudes of the fogs tell you about the mass scale of the halo population, or how many high mass halos you actually have. So having a measurement of the size of the fogs actually gives you cosmological information, which is very similar to the type of information you get from a cluster normalization constraint. So it's basically probing the halo mass function. Now, of course, this is the halo mass function convolved with your halo occupation function. But if you have a handle on what the halo occupation function actually is, then you can break the degeneracy and actually get complementary cosmological information from small scales to go with what you're getting from the coherent infall. So I'll skip this since we're going to go over that again. So obviously redshift space distortions by themselves can't really give you a good handle on what the halo occupation function is because there are too many degeneracies. So that's why all of our models start with WP, the projected correlation function. So here is the promised plot. This is WP is a function of the projected separation. The points here are the BOSS DR10 measurements. So we are constructing an emulator which is essentially centered on those measurements. So this already highlights one of the drawbacks of this sort of approach that Andrew mentioned, that this is a fine-tuned model. It is for this purpose. We could have made a more general model, but then we'd have to actually start adding more extra free parameters, and then you run into the other problems. So our goal was to make a BOSS-like emulator with a number density of about 4 times 10 to the minus 4. We do this through halo occupation modeling. Now, you would think that once you are beyond running the simulations and you can just explore HOD parameter space as big as you want, but once again, as Andrew pointed out, there's a practical limit that we're hitting, that the scaling of the Gaussian process is not very good. So we are limited to training samples of about 4,000 points, which luckily for us ends up actually being good enough for percent level predictions on the 2-point correlation function. But we're all going to be looking up and reading about hierarchical surrogate modeling tonight to hopefully get around this, because we're going to be adding more free parameters later. So In our halo occupation model, we have models that govern, or excuse me, parameters, free parameters that govern the halo occupation function, spatial bias within the halos, because they may be more or less concentrated than the dark matter, and velocity bias of the satellite galaxies and actual central galaxies within the halos, because they might not be moving as fast, or maybe even might even be moving faster than the dark matter. So this is the parameter space of our galaxy emulator. So these are the cosmological parameters here. These are the HOD parameters, and so there are 1, 2, 3, 4, 5, 6, 7 HOD parameters, which I thought made this a rather unwieldy number of parameters, but now it seems we're actually lagging behind some of the perturbation theory models. But don't worry, we're going to add some more extra free parameters to this about halfway through the talk. But one cosmological parameter I want to highlight is the thing called gamma F. That's not actually something in the simulations. That's really our target parameter. Gamma F is essentially a scaling factor on the halo velocity field. You can think of it as like scaling the growth rate. So F divided by FGR. This is what basically was constrained in the read it all paper. So you can think of this as either a way to constrain the growth rate, or you can think of this as a test of GR. If you, say, marginalize over all of the available cosmological parameter space from, say, available Planck data, hopefully gamma F is consistent with 1, which means that GR works. Or if it's not consistent with 1, it tells you that something is wrong and can tell you whether or not the velocity field is faster or slower than that predicted by GR. So we have this big training sample of data. We can train our Gaussian process, and we need to test that. So as Joe pointed out, we have these extra simulations, which are not included in the training sample. Each one of the cosmologies has 5 simulations as opposed to 1 for the training sample. So we have significantly higher statistical precision in our testing simulation. So we have tests for projected correlation function, monopole of RSD, quadrupole of RSD, and the points are the test simulations paired with some HOD model. And then the lines are the prediction of our emulator. And they're doing quite well, as you can see from here, but then you actually can look at the distribution of the errors. It's a little bit, there are gray contours here that you can't quite see. The gray contours is the actual distribution of errors of the model prediction versus the test data. And the training sample error is given by this red solid line. So the takeaway, which you can't quite see, but you just take my word for it, is that the emulator that we've implemented is actually doing as good or better than the sample variance of the simulations that we use, right? So you're actually getting a prediction which has higher statistical power than the original size of the boxes that you used to train the emulator. So if you then can analyze some RSD signal and you get projections on what you can get for constraints on F sigma 8, so let's just concentrate on this panel over here. So this is basically our target. This is the boss RSD value for F sigma 8 of about 10%. This is from DR11. Everything is volume matched to DR11 for various historical reasons. And the curves are showing what we get from the emulator. I think probably you should just concentrate on the red solid line. That's the fiducial predictions. And so what this curve is showing you is basically what are the constraints on F sigma 8 as you lower the minimum scale use. So the maximum scale here is always about 30 or 40 megaparsecs, which is why when the minimum constraint is 10 megaparsecs, you basically get no constraints at all. You do even worse than you do from the large scale perturbation theory analysis. But as you start including smaller and smaller scales, the F sigma 8 constraints get eventually match those that you get from the large scale analysis. And when you get inside of a couple of megaparsecs, actually get better than the constraints you get from the large scale perturbation theory analysis, getting to be about half, from 10% to about 5%. Now in Beth Reed's pilot study, she found that they got 2.5%, but we posited that was because it was fixing the cosmology. So this is Beth's result over here. And so when we use our emulator and fix the cosmology, or essentially just have really, really tight cosmological priors, and then just marginalize over the HOD parameters, we get about 2%. So we're showing that these basically are consistent. That's why these two disagree with each other. You get about a factor of 2 worse constraints when you actually include the different flexibility, when you actually include all the variations and all the cosmological parameters. So this is where we stand now. We are getting ready to apply this model to BOSS data. But before we do that, there are some important things that we need to add to the model. Namely, incorporating galaxy assembly bias. So this is all work that Zhangzhu has done. You met her earlier in the session. You should also go see his poster. And I think probably in this crowd, nobody really needs an introduction of what assembly bias is, but I just love this figure, so I'm gonna show them anyway. This is a slice through the Bolshoi simulation. These are at halos at 10 to the 11 solar masses. So the low mass halos, I'm cherry picking that because assembly bias is very high at that halo mass range. And these are the 5%, the halos with the 5% lowest concentration parameters, right? So these are the halos with the 5% highest concentration parameters. So I don't even have to show you a correlation function or a bias plot or anything for you just to immediately see that there's a very strong correlation between halo concentration and the large scale density field. And you can sum it up through a plot like this, where this is halo mass, this is bias. The black line is the mean bias as a function of halo mass, but now if you take those halos and break them up by various properties, you can see this secondary correlation, this assembly bias. So old halos are more clustered than young halos, which is essentially the same thing as the halo concentration assembly bias. Now, if you go the other way and you break things up by spin, at low halo masses, actually you get a very little assembly bias signal in spin, but now at high masses, you actually get a very strong assembly bias signal in spin. So there are lots of different halo properties which exhibit the secondary bias, which are correlated with the large scale density field. So for us analyzing galaxy surveys, the thing that we are concerned with is whether or not halo assembly bias goes into galaxy assembly bias. So galaxy assembly bias is just this question of, do galaxy properties at fixed halo mass correlate with these secondary halo properties that themselves show an assembly bias signal? So that means that the galaxies would show an assembly bias signal as well. This is actually what is predicted in many theoretical models, hydrodynamic and semi-analytic. I'm showing one example here. This is the stellar to halo mass relation from the Eagle simulation, which is a hydro simulation. And you can see how here at fixed halo mass, there is a correlation. The lower mass galaxies are in later forming halos, and the higher mass galaxies are in earlier forming halos. And so there's obviously going to be a difference in the clustering. Even though these are 10 to the 12 solar mass halos, these will be lower clustered, these will be higher clustered. And so this breaks the assumption of the standard HOD. The standard HOD is that halo occupation depends only on halo mass, but assembly bias breaks that. So the question is that there? If it is, you need to incorporate it. So if your concern is, I want to understand galaxy formation, like in this last plot, you would try and connect the halo properties to the galaxy properties. For cosmology, I'm going to take a much more objective approach and just skip all of the secondary halo properties and go straight to the large scale density field. So our assembly bias model is to change n-gal of m, so this is your mean halo occupation, number of galaxies as a function of halo mass, and add the secondary parameter. Now it's going to be number of galaxies as a function of halo mass and large scale density. So hopefully this should be flexible enough to incorporate whatever property happens to be the thing driving galaxy assembly bias, if galaxy assembly bias actually exists. So what we do is we take the HOD and essentially shift it either to higher masses or to lower masses, by this factor FHOD, depending on the large scale density. So these are different models that look like this. So this is large scale density, this is this shifting factor of the HOD, and here the purple line essentially shifts the HOD to higher halo masses at large scale densities. That essentially reduces galaxy formation efficiency at high densities. You have fewer numbers of galaxies in halos at high densities. Right? So what that does to the correlation function, this is now the effect of the projected correlation function as a function of scale, that suppresses clustering. The red line basically lowers the HOD, brings it back to lower masses at high densities. That increases the number of galaxies per halo in high densities, and therefore boosts up clustering. Right? So with this flexible parameterization, you get any signal you want. So the points with error bars is the assembly bias signal you get from an LRG-like sample, but it is created by abundance matching through V-peak abundance matching, right? And so V-peak has a little bit of assembly bias cooked into it because V-peak correlates with the large scale density field more than it correlates with the large scale density field. So you can see that there is an effect of a few % on the amplitude of the correlation function. It's not really severe, but it's there. And it is basically within the parameter space of our model. So if you can concoct some other sort of model for assembly bias, hopefully it'll be somewhere inside of our parameterization. So that's our goal here, is to make the most flexible parameterization you can possibly have. So not only do we want to compare to abundance matching, we want to actually test this model with abundance matching. So the previous tests we had were all with the test simulations in the Emulous. There's a bit of garbage in, garbage out on that because it's, you know, simulations done in the same manner with HOD applied in the same way. Now we want more of a non-parametric test of the emulator. So we're going to be test the emulator with the assembly bias model in it against VPeak abundance matching. Now, in addition to incorporating some amount of assembly bias, the abundance matching model also breaks a whole number of other assumptions that are inside of our HOD approach. First of all, there's no parameterized halo occupation function in abundance matching. The HOD can just look like whatever it wants to look like. Halos are no longer spherical when you actually look at halos in a real simulation. In the HOD, we are assuming that the velocity dispersions of the satellite galaxies are isothermal and Gaussian, and that is no longer true at high precision when you talk about subhalos in simulations. NFW is no longer exactly true. Satellites are no longer Poisson distributed when you talk about the subhalos, and of course we're including galaxy assembly bias. So we're breaking all of these assumptions in this test data with abundance matching. So this is now applying the emulator to abundance matching mock data and showing our parameter recovery of the three parameters that we really care about: omega matter, sigmate, and this F over FGR, or gamma F. And so you get unbiased parameter recovery in this case, in this case of using the VPeak abundance matching. So this is a good sign. I'm not going to tout this too much because this is, I believe, one of the multi-dark Planck boxes. So it's only 1 gigaparsec. So that's not a whole lot of volume, right? That's significantly less volume than the BOSS data itself. So what we would like to do is expand the amount of volume over, hopefully, an order of magnitude over which we can do this test to show that we are actually unbiased to a greater degree, as was talked about earlier in earlier sessions. Also, we want to test this against different types of abundance matching models, like what Joe is saying, this thing where you tune between VPeak and VVeer, where you can actually, in the abundance matching model, have a tunable parameter to turn up or down the amount of assembly bias. And with all of these different models, show that we can always recover unbiased cosmological parameters with the model. And then we know that we're good to go. So now that we at least feel that we have a reasonable working model, we can explore the impact of assembly bias with the emulator model itself, right? So this is WP, monopole, quadrupole, comparing a model with and without assembly bias. So the red is the standard approach. The blue is putting some amount of assembly bias in here. So we can characterize the amount of assembly bias by the ratio between the clustering with and without assembly bias. So this is an assembly bias model that decreases the clustering by 2%. So that, we're going to call that a very weak model, right? It's there, but it's not very strong. So if you try and constrain cosmological parameters, what happens? So this is, once again, omega matter, sigmate, and F, cosmological parameter constraints, analyzing this test data. It's a bit of a busy plot, but all you really need to do is compare the red to the purple, right? That's the assembly bias data, and we're going to apply a model that has no assembly bias in it and a model that does have assembly bias in it and see if there's any change. Well, at 2% effect in the amplitude of clustering, there's really no difference between these models, and you always get unbiased clustering. Now, however, if you have very strong assembly bias, so this is an assembly bias which changes the amplitude of clustering by about 20%. Now you can clearly see that if you have a model like the purple lines here, where you have your abundance matching model analyzing the mock data that has abundance matching in it, you get unbiased parameter constraints once again. But if you assume that there is no assembly bias and try and analyze this data, you get the purple contours, right? You get various large biases in your cosmological parameters, and also you get these very small you get these small contours, very tight parameter constraints. So a better way to show this is actually plotting the bias in the cosmological parameters, omega matter, sigmate, and gamma F, as a function of the amplitude of the assembly bias. So remember, 0 means no change in the clustering, And minus 35 means you're reducing the clustering by 35% through your assembly bias. So at less than 10%, change in the clustering, assembly bias isn't really affecting you. You can actually still analyze the data assuming no assembly bias and still get away with it. But when the change in the clustering is more than 10%, if you assume there's no assembly bias, even though there is, you get these very large biases in your cosmological parameters, and you get these unreasonably small error bars, mainly because the fits are no longer any good, right? So you get these very large chi-squares, so these are artificially small error bars. But for all of the different models, we're getting unbiased parameter recovery through the assembly bias emulator. So let's get that. So what is the best galaxy sample to actually do this sort of analysis on? So I pulled, this is, I think a version pulled out of the DESI final design report looking at constraints on F sigma 8 from the dark time survey and the bright time survey in DESI, and comparing it to 3 different types of models. Here you've got an F of R model, general relativity, and a DGP model. So essentially all 3 of these different models, you can parameterize them, or at least their growth rate of structure, as omega matter to the gamma, where general relativity is gamma of 0.55, and then these are just either raising or lowering the value of gamma. So even though the dark time has much more volume, so you get smaller error bars on F sigma 8, your ability to distinguish these models becomes more limited due to the fact that they all converge at high redshift. So you can pose a question of how well can you discriminate between the purple line and the gray line at these different redshifts. So this is a very convoluted plot. Just give me a moment to explain. The red line here is how volume changes as a function of redshift, right? So essentially at redshift 0.3, you have like 1/9 the amount of volume you have at redshift 1.5. And this gray line right here is your ability to differentiate between these 2 curves, right? So it's the change in F sigma 8 divided by the error you have on F sigma 8. Where here, all I am assuming about the error is that the error scales as the root of the volume, right? So at large redshift, you get more volume, but the models come together. At very small redshift, the models are diverging, but you have very small amount of volume, so you get very large error bars. So these 2 competing effects work against one another, but you get a peak in your differentiation power at around a redshift of about 0.5. So if you want to constrain gamma as your test of general relativity, your target redshift should be 0.5. But it doesn't change there, or it's not finalized there. This all assumes that volume is the only factor which is governing your ability to constrain F sigma 8. But one thing you get when you go to smaller redshifts is you get a higher number density. And if you're going to do this test at small scales, having a higher number density is very good. It lowers down the shot noise at small scale clustering measurements and allows you possibly even go to even smaller scales than you would have before. So this blue line right here is the DESI BGS number density. And it actually falls below, it's above the LRG number density up until a redshift of about 0.4. So this is a bit of a back of the envelope calculation, so many caveats apply, but I think it makes the point clear that if you take into account how the models differentiate, how much volume you actually have as a function of redshift, and what number density you can actually probe in a reasonable survey, when you now include the number density effect, the point where you can actually differentiate these 2 models the most is actually now around redshift of 0.25, right? The reason why the green model actually just stops and traces the red line, or excuse me, the gray line, is because once the number density dropped below the LRG number density, I just assumed it was the same as the LRG sample. So the best place to actually differentiate between different values of gamma is actually at low redshift, where the models spread apart the most, and you actually have the highest number density. So I guess I will just summarize here. We have constructed an emulator for nonlinear galaxy clustering that now we hope successfully implements assembly bias. And we can get unbiased parameter recovery. And the optimal galaxy sample for this type of analysis is going to be a high density sample at low redshift. So the bright galaxy sample in DESI is going to be pretty perfect for this. Although we don't want to put the cart before the horse, the next steps are implementing this model on BOS and EBOS data. All right, thank you.
One thing I learned from you, from your late 2000s papers, how much information content there is in pairwise velocity distribution.
Mm-hmm.
And I understand why in linear theory, people, I mean, the information that is available is contained in the monopole. Once you go to, once you sort of embrace simulation-based modeling as you have, like, that's no longer the case in the nonlinear regime. And so I'm wondering whether you can actually get significantly improved constraints, especially breaking degeneracies, and looking at pairwise velocity distribution instead of limiting yourself to the statistics that people limit themselves to in linear theory.
I am totally open to canning the multiples, or augmenting the multiples with all of its different clustering statistics. And I totally agree that now that everything is simulation based, we should not actually wed ourselves to these things which have long history in perturbation theory. We used to have this statistic, which was literally the length scale of the fogs. It was the distance along the line of sight you had to go before the correlation function fell by a factor of 2, which I had high hopes would be really good, but it ended up being really kind of more sensitive to the HOD than I thought it was going to be. So we wanted to develop statistics which were like, as independent of the HOD as you could possibly get. And like, say, monopole to quadrupole ratio is more insensitive to HOD than that particular statistic I'm talking about. So I'm in the market for other statistics and happy to hear any suggestions.
Just including more.
So Zhangju, you did the hexadecapole, right? And you found that it didn't give anything. So
you can answer this by direct computation. For example, think about that compute in your parameter space and then just manually calculate a bunch of pairwise velocity distributions and then take a PC down decomposition and then you thereby construct like maximally informed numbers. I would think in terms of constraining HOD, you could go on water or anything that becomes linear. I don't know.
But what's the exact observable though of that?
Pairwise velocity distribution as a function of both scale and mass selected test. It's HOD that's fixed mass spin, but it's still the distribution of pairwise velocities.
But if I don't know the intrinsic distances, how do I get the pairwise velocities? Well, we should talk about it more offline.
Yeah, I have a short comment about these fingers of God. So we have done some tests. Ultimately, the goal is to reconstruct the initial density field, right? So
that's not my goal.
Okay, that's very well. Okay, this is all of us. Okay, so we have found that the density field with fingers of God is fully uncorrelated with the initial density field. Okay, that's why, given this, I said that we believe that fingers of God contain zero explosive information. So, do you agree with this?
Oh well, I didn't mean the comment to be disparaging. I kind of meant it to be more of a joke. But I think it kind of depends on what viewpoint you have and what direction you're approaching things. I mean, my statement's that if you take all halos, like if you change omega matter and increase it by some amount, all halos just get more massive by that amount, and the fingers of God are going to get larger by the mass to some power, right? So in that sense, you get omega matter information by the length scales of the fogs, right? Or if you change sigma 8 and you have more high mass halos, you're going to get bigger fogs. You're always going to get now how that traces the initial density field, if there's zero correlation, I guess that's true, but that doesn't mean that it's not giving you cosmological information because it's telling you about the populations of the halos.
but then I think that the most important question is how to make sure that this information is not degenerate for some galaxy formation physics. Because this statement is a bit like n bar. Okay, n bar depends on cosmology. We know if I had a different cosmology, my n bar would be different. But then somehow nobody tried to measure organic matter from n bar, right? From the number density.
Right.
In principle, like there are some semi-analytical approaches, right? We have the mass function. We can try to also get some sigma from the n bar. Okay, but what is the constraint on sigma 8 from 1 over m bar? Both has measured 1 over m. What is the constraint?
But this is the whole reason you do HOD. You are marginalizing over the different physics available to you.
Normally, yeah, we're marginalizing all this. Yeah, because just
Okay, let's
okay, maybe we can
go to that. Okay, one last question. Okay.
Very nice talk. I'm absolutely totally in favor of this approach. And actually, just to probably know this paper we made more than a year ago, just using two simulations, keeping just with sham to one simulation with a standard lambda CDN, one modified RPF for one simulation. Very small, unfortunately, but with good resolution. Those are confirmed. And we've got very clear indications that very small deviations from GR get galaxies going to be crazy on small scale. But apart from this, my question was, when you did the validation with the sham of your model, how did you implement the effect of the time dependence of your halos? How do you call it? Just missing the English word.
Formation history time.
Assembly bias, yes. How do you take into account the assembly bias of the sham? When you rank your halos and your galaxies to actually match.
You mean to make the mock data? Mm-hmm. So the rank ordering of okay, the rank in the sham or in the abundance matching, the rank ordering of the halos is done by V peak, right? So and that imparts an assembly bias onto the galaxy population just by using V peak and not using, say, M peak or mass today.
Okay, so that means if you use V peak, the assembly bias is
well, remember that's only the testing data. That's not in the emulator model at all.
So the reason I'm asking is because we use the sham.
Mm-hmm.
Incredibly beautiful. That's why I'm asking, how much are we getting wrong because we don't count or are we taking into account?
Well, so here, these are the two different colors are if you do or do not assume assembly bias in your model, even though there's a little bit of assembly bias in the data, and you're getting unbiased parameter recovery if the change in the amplitude from the assembly bias is a few percent, and V peak abundance matching is just a few percent. So the data is, well, no. This over here is entirely 100% all HOD based, right? That's what allows us to have full parameter coverage of different types of assembly bias. So that is, once again, like the way I make the model is the same way I'm making the test data. So that this is just exploring parameter space as opposed to proving that the model is unbiased.